Air tools use compressed air to do a number of tasks. Air can come out of a pneumatic tool with a lot of force, and that can cause damage and injury. So before using an air tool, it's important to check all of its connections are secure and the hoses are in good condition and not leaking. It must be lubricated before it's used. This may be done automatically by an inline oil mister that puts a mist of oil in the air supply. Or it may need some squirts of light oil into the air inlet fitting. This model also removes moisture from the air before it's fed to the tools. The most common pneumatic tool in an automotive workshop is the air impact wrench. It's sometimes called a rattle gun. It's easy to hear why. Taking the wheels off a car to replace the tyres is a typical application for this air tool. It often needs a lot of torque to twist the nuts free. The rattle gun can be set to spin in either direction, and this valve controls how much torque it applies. It should never be used for finely tightening wheel nuts. There's a real danger of doing them up much too tight. That could cause the bolts to fail and the wheel shear off the vehicle while it's moving. Another rule with the air impact wrench is to use only these specially hardened impact sockets, extensions and joints. The sockets are special 6-point types, and these flats can stand the sudden force that the rattle gun provides. This is an air ratchet. It uses the force of compressed air to turn a ratchet drive. It's used on smaller nuts and bolts. Once the nut is loosened, the air ratchet spins it off in a fraction of the time it would take by hand. This is an air chisel. It's useful for driving and cutting. The extra force that's generated by the compressed air makes it more efficient than a hand chisel and hammer. Just as there are many chisels, there are many bits that fit into the air chisel, depending on the job at hand. This is an air drill. It has some important advantages over the more common electric power drill. With the right attachment, it can drill holes, grind, polish, and clean parts. Unlike the electric drill, it doesn't run the risk of producing sparks, which is important around flammable liquids or petrol tanks. An air drill doesn't trail a live electric cable behind it, which could be cut and cause shock and burns. And an air drill also doesn't get hot with heavy use. This is the simplest air tool. It's a blowgun or air duster. It's really just compressed air by itself, controlled by a lever or valve. It's used to blast debris and dirt out of confined spaces. That can be dangerous, so eye protection must be worn whenever it's used. Noise levels are usually high, so ear protection should also be worn. It's also dangerous to use it to clean yourself down. Its blast should always be directed away from the user and anyone else working nearby. This is the most common kind of chisel, a flat chisel. It's made of high-quality steel, and the end is tempered and hardened because it has to be harder than any of the metals you're likely to want to cut with it. The head needs to be softer, so it won't chip when it's hit with a hammer. Safety goggles should always be used. This nut is so corroded it's frozen onto the bolt. In this case, the nut and bolt will be thrown away, so a chisel can be used to remove them. A hacksaw could get the nut off, but a flat chisel is preferable. The hammer should be much heavier than the chisel, so it won't bounce back or cause jarring. As the chisel goes to work, it helps to avoid damage by checking where metal chips are likely to fly. A couple of sharp blows and it's off. This is a crosscut chisel. It's called crosscut because the sharpened edge is across the blade width. This chisel narrows down along the stock, so it's good for getting in grooves. It's used for cleaning out or even making keyways. The flying chips of metal should always be directed away from the user. This is an air ratchet. It uses the force of compressed air to turn a ratchet drive. It's used on smaller nuts and bolts. Once the nut is loosened, the air ratchet spins it off in a fraction of the time it would take by hand. This is a portable drill. This one has a cord you have to plug into an electrical supply. Cordless models use their own internal batteries. When you can't bring the work to the drill, you can take this drill to the work. But don't expect it to put large holes through very hard metal. The biggest drill bit that'll fit in the chuck here is usually marked on the body of the drill, along with the speeds at which it turns. There are usually 2 speeds, but some drills can be set to any speed within their range. A bench-mounted drill allows accurate drilling with more control, more so than a portable drill, which is convenient but can be difficult to guide accurately. A mounted drill can feed the drill bit at a controlled rate, and the work table secures the job at a constant angle to the drill bit. Also, this drill can be set to run at different drilling speeds. This drill chuck takes bits up to 13 millimeters in diameter. Drill bits come in many closely spaced sizes. The most common is the twist drill. It has a point and a body, usually with 2 spiral grooves. And its shank is gripped in the jaws of the drill chuck. A Morse taper is a system for securing drills. Morse taper size changes according to drill size. The shank of the drill bit is tapered, and it fits snugly into the drill spindle, which has a similar taper. This tang is also located in the spindle, and it drives the drill. It's a quick way to change drills without constantly adjusting the chuck. When there's already a hole drilled in sheet metal that needs enlarging, a multi-fluted tapered hole drill will do the job in about the same time it takes to say it. A drilling speed chart should be kept near the bench or pedestal drill. It compares drill sizes and metals to show the proper speed. So to drill a 10mm hole through this piece of aluminium, the drill speed should be 1,800 revs per minute. Screws are generally smaller than bolts. They can have a variety of heads. They're used on smaller components, and often their thread extends right from the tip to the head, so they can hold together components of different thicknesses. Different screws can be tightened with a range of tools. This is an Allen head screw with a recess for an Allen key. It's sometimes called a cap screw. It usually screws into a hole rather than a nut, and it needs a small spanner. This is a machine screw. It has a slot for a screwdriver. Bolts are always threaded into a nut or hole that's got an identical thread cut inside. But a couple of special screws cut their own threads as they go. This is called tapping a thread, and this is a self-tapping screw. It's made of hard material that cuts a mirror image of itself into the hole as you turn it. This is also known as a self-tapping screw, but it's designed for cutting and holding thin sheet metal, so it's often used on car bodies. Bolts are often bigger than screws and are used for heavier jobs. They nearly always have hexagonal heads that only fit spanners, or Torx drivers for these Torx bolts. Often the thread on a bolt is only as long as it needs to be to tighten onto the nut or into the threaded hole. A stud is like two bolts in one. The exhaust manifold on the cylinder head is located and held by studs. Studs can have different threads on each end. On this end, there's one that's best for gripping the hole in the exhaust manifold, and on the other end, there's a thread for pulling everything together tightly with a steel nut. Nuts are often used with bolts. A nut is a piece of metal, usually hexagonal, with a thread cut through it. There are many different ways to keep it done up tightly. This self-locking nut can have a plastic or nylon insert. Tightening the bolt squeezes it into the insert, where it resists any movement. The self-locker is highly resistant to being loosened by the kind of vibration that engines and vehicles experience. Tightening this style of nut distorts the insert, so it only provides its locking effect the first time you use it. If you remove the nut, replace it with a new one. More secure still is this castellated nut with slots like towers on a castle. When it's screwed onto a bolt that's been drilled in the right spot, a split pin can be passed through them both and then spread open to lock the nut in place. A speed nut isn't as strong as the others, but it can be a fast and convenient way to secure a screw. Once the speed nut is started, it doesn't need to be held. Some bolts and nuts need washers. Flat washers spread the load of a bolt head or a nut as it's tightened and distribute it over a greater area. This protects the surface underneath from being marked by the nut or head as it turns and tightens down. Flat washers should always be used to protect aluminium alloy. Other washers tackle the problem of nuts working loose through vibration or movement. A spring washer compresses as the nut tightens, and the nut is spring-loaded against this surface, which makes it unlikely to work loose. The ends of the spring washer also bite into the metal. Spring washers are used more for bolts and nuts. Screws mostly rely on smaller shake-proof washers. The external ones have teeth on the outside, the internal ones on the inside, and one has both. Tab washers get their name from these extensions. After the nut or bolt has been tightened, they remain exposed and are folded up to grip the flats and prevent movement. Chemical compounds help prevent fasteners loosening. They're applied to one thread, then the other is screwed onto it. This creates a strong bond between them, but one that stays plastic, so in future they can be separated with a spanner if necessary. Other compounds can be applied after assembly. Some metals react with each other and bind together. Spark plugs can do it when they're in aluminium cylinder heads. Anti-seize compound neutralizes the chemical reaction that can make this happen, and it prevents threads and fasteners from sticking together. Larger bolts and nuts must sometimes be tightened to a specified level, tight enough to hold components together, but not so tight that the component or the fastener could fail. This level of tightness is called a torque specification. Bolts and nuts are often marked to tell you how strong they are, how much torque can be safely applied to them. This is a grade 5 bolt, as these markings show. This is a grade 8 bolt, so it can be done up more tightly without danger of it failing. The dots on this nut give similar information. This is a grade 8. These are imperial system markings. The metric system uses numbers stamped on the heads of metric bolts and on the face of metric nuts. Even studs have a marking system to make sure they're not overstressed when you tighten them. Files are often sold without handles, but they shouldn't be used until a handle of the right size has been fitted. The handle should be checked before use. It can come loose, and it may need a sharp rap to tighten it up. Clean hands will help avoid slipping. Hands should always be kept away from the surface of the file and the metal that's being worked on. Filing can produce small slithers of metal which can be difficult to remove from a finger or hand. And acids and moisture from the skin can cause corrosion. What makes one file different from another is not just its shape, but how much material it's designed to remove with each stroke. That depends on the teeth. These are both flat files, the most common general purpose type, but their teeth are different. The teeth on this coarse grade file are longer, with a greater space between them. Filing this piece of mild steel removes a lot of material with each stroke. A coarse file leaves a rough finish. This is a flat file, but its shorter teeth remove much less material on each stroke, and the finish is much smoother. On a job, the coarse file is used first to remove material quickly. Then a smoother file gently removes the last of it and leaves a clean finish to the work. The full list of grades in flat files from rough to smooth is rough, coarse bastard, second cut, smooth, and dead smooth. Some flat files are available with one smooth edge, called safe edge files. They allow filing up to an edge without damaging it. Flat files are fine on straightforward jobs, but files need to be able to work in some awkward spots as well. warding file is thinner than normal for working in narrow slots. A square file has teeth on all 4 sides, so you can use it in a square or rectangular hole. A square file can make the right shape for a square metal key to fit in a slot. This is a 3-square file. It's triangular in section, so it can get into internal corners. Curved files are either half round or round. This is a half round. Its shallow convex surface can file in a concave hollow or in an acute internal corner. The fully round file, sometimes called a rat tail file, can make holes bigger. Or it can file inside a concave surface with a tight radius. This is a thread file. It cleans clogged or distorted threads. It has 8 different surfaces that match different thread dimensions, so the right face must be used. Files should be cleaned after use. If they're clogged, they can be cleaned by a tool that's really part of the family called a file card or file brush. Depending on how hard or soft a material is, a special file may be needed. It's no good trying to file something if the file is softer than what is being filed. And softer metals like copper and aluminium can clog a conventional file. Tools that measure the difference between any 2 points can be divided up according to how accurately they do it. A measuring tape is useful for checking spring sag. A steel rule is capable of accurate measurement down to a millimetre. The graduations must stay as close as possible to the points being measured, and the rule must be read as close to square on to the scale as possible. If a distance needs to be measured with a high degree of accuracy, vernier calipers can be used. The sliding jaw grips the surfaces being measured on the outside, or for an internal measurement with these jaws on the inside. Depth can also be measured with the end of the caliper slide. Once the measurement is taken, this screw locks it in. Inches or millimetres are read here, and the fractions on this vernier. That gives this the name of vernier calipers. Other calipers show the fractions on a dial or an electronic readout. This is a precision instrument that'll measure down to 2/100ths of a millimetre or 1/1000th of an inch. For the highest accuracy in measuring distances, micrometers are used. Like calipers, they can measure an outside dimension, inside, or depth. But a different mic, as they're called, is needed for each task. This is an outside micrometer, the most common one. The object to be measured is nipped very lightly between the anvil, the part that stays still, and the spindle which moves towards it on a very fine thread. The distance between them is read off the scale on the barrel, down to the finest fraction, which is read off the scale that turns on the thimble. For inside measurements, this inside micrometer works on the same principles as the outside micrometer, and so does this depth micrometer. They give a very accurate readout of even the tiniest movement of a very finely threaded spindle. They must be kept clean, especially along surfaces that do the measuring. They should read 0 when fully closed, and be checked and adjusted as described in the instructions that come with them. For measuring distances in awkward spots like the bottom of a deep cylinder, this telescopic bore gauge has spring-loaded plungers that can be unlocked with this screw, so they slide out and touch the walls of the cylinder. The screw then locks them in that position. The gauge can be withdrawn, and the distance across the plungers can be measured with a micrometer or calipers to convey the diameter of the cylinder at that point. In automotive workshops, clearances and narrow gaps often need to be measured. This is done with a set of feeler gauges. The markings on these strips show they're graded from fractions of a millimetre up to a few millimetres. They're used by finding one that fits smoothly in the gap being measured. Sometimes the best fit must be made by using a combination. Then the measurement is the total thickness of all the gauges that fitted into the gap. Roundness and squareness sometimes need measuring. This crankshaft can be rotated in these V-blocks. If it's bent, it will show on the dial gauge. It senses slight movement at its tip and magnifies it into a measurable swing on the dial. To check whether something is square, parallel, flat or true, a straight edge is used. It's placed against the surface that needs checking. This tri-square is a rectangular blade fitted at precisely 90 degrees to a solid stock. A simple idea and simple to use. The most common hammer in an automotive workshop is the ball peen or engineer's hammer. Like most hammers, its head is hardened steel. A punch or a chisel can be driven with this flat face. Its name comes from the ball peen or rounded face. It's usually used for flattening or peening a rivet. The hammer should always match the size of the job, and it's better to use one that's too big rather than too small. This is a soft face hammer. Hitting chisels with a steel hammer is fine, but sometimes you need just to tap a component to position it. A steel hammer might mark or damage it, especially if it's made of a softer metal like aluminium. What you use is a soft face hammer. Some are very soft with rubber or plastic heads, through to those using brass or copper. When a large chisel needs a really strong blow, it's time to use the lump hammer. It's like a small mallet with two square faces made of high carbon steel. It's the heaviest hammer that's used one-handed. The most common mallet in the workshop has a head made of hard rubber. It's a special purpose tool used most often for fitting tyres onto rims. This is a dead blow hammer. It's designed not to bounce back when it hits something. A rebounding hammer can be dangerous or destructive. Its head is either made of lead or it's hollow with lead shot inside. The lead absorbs the blow. Making sharp, clean lines on metal requires a sharp, clean point. This is a scriber. It's made from hardened and tempered tool steel. To mark a line with a scriber, draw it towards you and keep it angled in the direction it's going to travel so it doesn't dig into the surface being marked. On some hard or shiny surfaces, scribe marks can be hard to see, so marking dye helps. A thin coat is applied to the area being marked. It dries very quickly. Then the path cut by the point of the scriber is easy to see. Engineer's blue is similar to marking dye. It comes in tubes and it's a bit like blue butter. Sometimes in checking a fit or testing for flatness, it's difficult to see the area being worked on. By smearing a small amount of engineer's blue on a surface plate, it can be used to indicate if the surface to be tested is flat. The blue marks on the housing indicate the high areas which must be removed to obtain a flat surface. A flat surface would be blue over the whole surface. The flaring tool has two parts: a set of bars with holes that match the diameter of the pipe end to be shaped, and a yoke that drives this cone into the mouth of the tube. The two most common shapes are a single flare, for pipes carrying low pressures like a fuel line, and the double flare for higher pressures such as in a brake system. To make a single flare, start with the pipe level with the top of the flaring bars. With the clamp screw firmly tightened, the feed screw flares the end of the tube. Making a double flare is similar, but more of the tube is exposed to allow for the folding over into a double flare. This double flaring button now goes into the end of the tube. The double flare button comes out, and the pipe looks like this. Turning the feed screw completes the forming of the double flare. A pipe cutter is more convenient and neater than a saw when cutting pipes and metal tubing. This sharpened wheel does the cutting. As the tool turns around the pipe, this screw increases the pressure, driving the wheel deeper and deeper through the pipe until it finally cuts right through. There is a larger version that's used for cutting exhaust pipes. When applying pressure to pliers, make sure your hands aren't greasy. Otherwise, sooner or later, they're going to slip. Select the right type and size of pliers for the job. As with most tools, if you have to exert almost all of your strength to get something done, then you're using the wrong tool, or you're doing it incorrectly. If it lets go, you're going to get hurt. At least, you'll damage the tool and the work. Pliers get a lot of hard use in the workshop, so they do get worn and damaged. That makes them inefficient and even dangerous. Always check the state of all workshop tools on a regular basis. Combination pliers are made from two pieces of high carbon or alloy steel. They pivot together so that any force applied to the handles is multiplied in the strong jaws. Some pliers provide a powerful grip on objects, others are designed to cut. Combination pliers can do both. That's why they're the most common type. There are two surfaces for gripping flat or rounded objects, and two pairs of cutters. The cutters in the jaws should be used for softer materials that won't damage the blades. These cutters next to the pivot can shear through hard, thin materials, like steel wire or pins. Most pliers are limited by their size in what they can grip. Beyond a certain point, the handles are spread too wide, or the jaws can't open wide enough. But these multi-grips overcome that with a movable pivot. A pair of multi-grips can get a comfortable grip on a range of objects, and there are two surfaces for things that are flat or round. Vice grips are general-purpose pliers. Put an object between the jaws. Turn this screw until the handles are almost closed, then squeeze them together to lock shut. They can also be used as temporary clamps in case a free hand is needed elsewhere. There are a few specialized pliers in most workshops. These long-nosed pliers can reach tight spots that others can't. Circlip pliers have metal pins that fit in holes in a circlip. Squeezing the pliers compresses the circlip and fits it in its groove. There's also a special pair of external circlips that are sprung to push them open. These cutters are called nippers or pincer pliers. They have a cutting edge at right angles to their length. They get a grip on and cut through anything sticking out from a surface. Rolling them on the curve of the jaws gives leverage too. Side cutters work with any length, say a piece of wire or a steel pin. They're the most common cutters in the toolbox, but they shouldn't be used on hard or heavy gauge materials. Bolt cutters cut heavy wire, rods and bolts. Their compound joints and long handles give the leverage and cutting pressure that's needed for heavy gauge materials. Tin snips are the nearest thing in the toolbox to a pair of scissors. They can cut thin sheet metal, and lighter versions make it easy to follow the outline of gaskets. Most snips come with straight blades, but if there's an unusual shape to cut, there is a pair with left or right hand curved blades. Aviation snips are designed to cut soft metals. They're easy to use because the handles are spring-loaded open and double pivoted for extra leverage.